Excellent. Hi, everyone. I just want to start by saying thank you to the organisers for giving me the opportunity to come to talk to you today about some of the really exciting work that we're doing using remote sensing. So one of the tools that we have, as Jamie described, to try to probe the composition of the planet building environments around nearby young stars. So because I only have 15 minutes with you today, I'll focus mainly on the results from this ALMA large program here called Molecules with ALMA at Planet Forming Scales. So our simplest picture, if you like, of the chemistry of planet formation, although Thomas will no doubt tell us a lot more in the next talk, is here we have an artist's impression of a protoplanetary disk. And these structures arise naturally through mass and angular momentum conservation as a young star forms. And you can see very clearly here, we have a boundary between kind of this inner region and this outer region. And this boundary is what we call the snow line. This is a very important region also for stimulating planet formation, but it also kind of discriminates between the inner rocky planet forming zone where we don't have volatiles in solid form. We only have them in gas form, and kind of the outer gas giant planet formation zone where we have some moons and other kind of potentially habitable environments out there as well. So out beyond the snow line, the temperature in disks is cold enough that we can freeze out molecules like water onto the surfaces of dust grains, giving us also that reservoir that we need for building gas giant planets and also comets as well. So why is this kind of important for kind of setting habitability conditions? Well, we know, I think as Jamie had said, and others and Emmanuel as well, we think that delivery of volatile material and organic material from impacts likely help to shape the habitability of the young Earth. And of course, comets, as we know, visit the inner solar system, and if they're able to pass through the snow line, you can also get transport of that volatile rich material, then can get processed into rocky bodies in the form of kind of those meteorites, as Jamie had also said. So kind of a very simple picture of the protoplanetary disk discriminating between the inner rocky planet building zone and the outer gas giant planet building zone, but also where we have a very rich reservoir of volatile material as well. So comets are kind of an important source of information for us because we think that they contain some of the most pristine material that we have left over from planet formation in our own solar system. And we know from remote sensing of comets, but also in situ observations, also with, for example, the Rosetta mission, we know that these comets are rich in what we call complex organic molecules. So these molecules are kind of a step up from the very simple diatomic, triatomic molecules that we see in the diffuse interstellar medium. And one question that we can ask ourselves is, do we see these same ingredients that are kind of preserved in the cometary record in the comet forming environments around other stars, you know, provided that this picture that we have of the planet forming environment persists in all stars? So to do these types of observations and measurements, we use this wonderful telescope here, the Atacama Large Millimeter Submillimeter Array. And this is an interferometer that operates at millimeter wavelengths, or around 300 gigahertz if frequency is more your thing. And what we can do with ALMA, it's an array of 66 dishes. We can use that as one big giant telescope, and really allows us to get down to the resolution that we need to probe the dust distribution in the planet forming regions around other stars, but also it has a sensitivity and spectral resolution for us to look at line emission coming from molecules. And this is right at the right wavelength that we need for seeing rotational transitions of molecules from simple to complex. In gas, it's around 10 to of order 100 Kelvin or so. So it's just the right temperature regime that we're probing with these observations as well. So there's been decades of work really looking at the molecular composition of protoplanetary disks from single dish all the way up to the interferometric age. And what that showed us is that disks are rich in kind of especially simple organic molecules, so carbon-bearing molecules like carbon monoxide, and we also see molecules like C2H. And in the infrared, we can see things like methane and acetylene. But it was really only with ALMA that we had the resolution and sensitivity to start to really look for bigger molecules. So this motivated an ALMA large program back a few years ago now. It was 130 hours that we were granted. We looked at 20 different molecules in 5 protoplanetary disks with ALMA. And we really tried to, the reason we needed 130 hours is that we wanted to get down to the resolution that we were really seeing within that planet building zone, so within around 50 astronomical units or so in our sources. Of course, with 130 hours of time, we had a huge number of different science goals and science focus that we could get with this data. You can see here that we wanted to look at the relationship between the kind of the structure induced by forming planets and the chemistry that's ongoing in there. We wanted to find out something about the vertical distribution of molecules and disks as well. So we tend to think of everything exciting related to planet formation as happening in the midplane. But these disks aren't flat structures. They actually have some vertical extent that's driven by heating from the central star. So we wanted to, probe kind of where vertically, kind of in what we call the disk atmosphere, these molecules that we knew were there and were residing as well. But for the purposes of this talk, I'm just going to focus on one key question that we had was, what's the distribution of organics in the planet forming region? And in particular, I'm going to focus on kind of those large organics. So molecules that have 2 or 3 carbons that kind of bridge that gap, if you like, between the very simple molecules that we have in the diffuse interstellar medium and those much more complex molecules that Jamie was talking about that we see in meteorites. So the 5 sources that we chose are 5 nearby protoplanetary disks that had already been well detected in molecular lines with lower resolution data. And what you're looking at here are 5 sources, and you're looking at the continuum emission, which is tracing the dust distribution in the disk to first order. And this is at about 1 millimeter in wavelengths. And the scale bar that you see in each of these images is about 20 astronomical units. And the little bar, the little ellipse that you see in the bottom left corner gives you a sense of the resolution of these images. And we chose these 5 sources for multiple reasons. We wanted to make sure we were kind of spanning a range of ages and masses of disk hosting stars. So not just, solar mass stars, but also looking at kind of warmer disks around A-type stars as well. We wanted to probe disks that had a range of different substructures that you can see here visible in the dust emission. So you can see these kind of beautiful, almost concentric rings of dust that we see. That one theory is that these are being sculpted by forming planets, but there's other physical origins for these dust substructures as well. And we wanted to probe disks that had gaps, some that didn't have gaps, and some that were kind of larger in continuum extent, and some that were a bit more compact. So while it's not a statistically meaningful sample, we tried to kind of pick 5 sources that kind of give us a span of different properties of known disk hosting stars. So just to give you an idea of what our data look like, so I'm going to show you kind of an array of images which shows you the chemical diversity that we see just within a single source. And this is the disk around the nearby young Herbig star, HD 163296. And this is what the MAPS data look like. So every image that you see here is a different molecular face of this protoplanetary disk. So you see here the molecule that we're probing and also the rotational transition that we're probing as well. And you can see if you look closely, we actually have multiple transitions for some of the molecules that we have targeted. We also have some organic molecules, so we have HCN, C2H here, and we also have some larger molecules as well, so things like methyl cyanide. We have hydrocarbon chains like cyclopropionylidene, and also oxygen-bearing kind of larger molecules as well, like formaldehyde. And just to give you a sense of scale of how big the molecular disks are, I just show you the continuum here on the same scale as well. So the continuum is significantly more compact than the molecular emission. So kind of the take-home message from this array of images is that the disk looks very different in all of the molecular tracers that we targeted. We see some that don't have little hints of substructures, some like HCN, C2H that actually are highly structured. some of which is sometimes coincident with the dust emission, sometimes not. So the disk looks very, very different in each of these molecular tracers. So we see this huge diversity of chemical substructure and not necessarily any consistent correlation with the dust structure. That's giving us information that there's a lot of physical processes that are happening in the disk that's kind of shaping its composition and then originating in these sometimes very highly structured molecular line images. Just to give you an idea as well of the kind of chemical diversity that we see across sources. So here we have our 5 disks going from IM-Loop, which is the youngest and lowest mass, up to MWC 480, which is the oldest and the highest mass. And then we have 4 different molecular tracers. We have 13CO, hydrogen cyanide, HC3N, and then formaldehyde, H2CO. And again, you see that not only does a single disk look very different in the different molecular tracers, the disks themselves all look different from each other. A very good example of this is 163296, where the hydrogen cyanide is very highly structured. But if we look at IM-Loop, it's actually a lot more extended. That's similar kind of for formaldehyde as well in IM-Loop and AS209, where the formaldehyde is much more compact rather than extended. So we see that each molecule in each disk has a different behavior. And again, this is giving us hints that kind of the chemistry of each of these disks is quite unique in itself and arises from multiple sources. So irradiation, ionization, snow lines are likely playing a role, but also we think transport, as in mass transport of material across and through the disk, is likely also shaping what we're seeing. So just to finish, I want to focus in on the organic reservoir, which was the focus of the talk. So here we have this nice schematic of where disks in their planetary systems arise from around young stars. We have our molecular cloud, which collapses under gravity and rotation to form an orbiting disk-like structure that then eventually the envelope clears, leaving behind an optically visible star with a surrounding protoplanetary disk within which a planetary system will form. Now, what we know from, again, a few decades of observations, if we look at cold clouds, if we look at the warm environments around protostars and also in comets as well, as they sublimate their coma, all of these environments are actually quite rich in complex organic molecules. So there's a chemistry that can occur in these environments that kind of leads naturally to pretty substantial abundances sometimes of these organic molecules. But we really haven't been able to extend that knowledge of the chemistry in those environments down into the protoplanetary disk. And this is again what one of the focuses of the MAPS program was. So what you're looking at here is again our continuum images at the top here, looking at our 5 sources. And then I show you the work that we led here in Leeds, which is looking at the largest molecules that we had in our sample. So that's HC3N, which is 3 carbons, CH3CN, methyl cyanide with 2 carbons, and cyclopropionylidene, which is a hydrocarbon, C3H2. And I show you these side by side. So we can see that in some cases, the molecules do have quite a lot of substructure. In IM-Loop, we don't really detect very much at all. It seems to be poorer in these organic compounds than our other 4 disks, which is interesting. You can see that the emission that we're picking up from these larger molecules is much more compact than some of the other molecules that I showed you, like CO and formaldehyde. And we think this might be related to the fact that we think that the larger dust grains that have kind of become more compact and kind of sculpted and shaped by the processes occurring in the disk might actually have brought in those organic molecules from the outer disk and perhaps enhanced their abundances in the inner planet forming region. So we think we're seeing some evidence either directly or indirectly for the larger grains that are hosting the ices actually being concentrated towards the mid-plane and pulled inwards towards the planet forming region. So that's what I mean by these kinds of mass transport processes. So the molecules that I showed you, we can actually do some empirical mapping to try to figure out where their vertical emitting layer is. So we do this by exploiting the whole suite of observations that we have, by empirically mapping the temperature structure of the disk, by using multiple lines to get an excitation information, and then using that excitation information to kind of layer on our empirical temperature map where our molecules are actually emitting from. And this is what I'm showing on here. So you have the radius on the x-axis and the height away from the midplane on the the y-axis. And then the contours show you the temperature structure of the 4 discs. In blue, we have where the HC3N is sitting, and in red, we have where the methyl cyanide, the CH3CN, is sitting. And you can see in some cases, we are actually getting quite deep down into the midplane. So in particular, we seem to be tracing quite deep down in these 3 discs with methyl cyanide down into where the millimeter dust is sitting as well. And we tend to find more generally that the HC3N is sitting much higher up in the disk and higher up in the atmosphere, maybe triggered by the chemistry that's happening up in the disk atmosphere. So we see this great diversity also in the vertical structure, but with some of these observations, we are actually able to probe quite deep down in the disk. So we can take our analysis one step further and we can do a comparison with solar system comets. So in the 4 disks where we detect all the large organics, I show you here the ratio of HC3N with respect to HCN and the ratio of methyl cyanide with respect to HCN as a function of radius for our 4 sources. In the pinky orangey color, you can see the cometary range that we've measured within the cometary record. And in blue, we have the ratios that we've derived from the observations. So hopefully you can see that for a lot of our disks, the blue range is sitting within the orange range and is also spanning the range as well for the 4 disks. So this kind of tells us that these abundance ratios of these larger cyanides with respect to HCN actually align really well with the range in comet measurements. And then finally, the last thing that we kind of did was we tried to sum up, which is quite a difficult job to do. We tried to sum up everything that we had within kind of the 50 AU region within each disk. And this is a table with a lot of numbers, but I just want you to focus on these 2 columns that we have here. So we summed up for the 5 disks, the percentage that we had, percentage of molecules that we had in nitriles with respect to water, and then also all organics as well, anything that's carbon bearing with respect to water. And then we compared that with what we know from Comet 67P, for which we have kind of the biggest inventory, if you like, of what that comet is made out of. And you can see that with the exception of AS209 and IM loop, all the other 3 disks are actually matched really well, to an order of magnitude to 1% or so of what we see in the cometary record. So the organics that we see in the planet forming regions around these young disks, the amount of those organics with respect to water, again, is in pretty good agreement with what we see in comets. So just to finish, I showed you the first results from an ALMA large program that we dedicated to disk chemistry in the planet forming zone. You can see that we see this huge diversity of chemical substructure that we're still wrapping our heads around and still trying to understand. The large organic molecules that we detected are well detected on 4 out of 5 of our sources, and we think is showing possible evidence of transport through the disk. The organic inventory that we measure overlaps with that also in the comet reservoir. And then finally, we can kind of say broadly that so far with everything that we've probed, the comet forming zones of nearby young stars have the same ingredients as revealed in the cometary record in our solar system. So just a little advertisement, we have 20 papers out. They're now in press in a special issue of the Astrophysical Journal supplement series. We also have a website as well, and you're very welcome to go there. You'll see all the publications, you can access the data. We're actually making everything, all of the data products publicly available through that website. And then just to finish, a lot of this work was led by younger researchers, and we would not have been able to do our special issue of Astrophysical Journal supplement series without their great efforts. So I just wanted to say a thank you to them, and I'll stop talking now. Thank you.